So I'm Alex Bronstein, and this is a course on digital image processing. Basically, the goals or the content of this class, at least this is wishful thinking. This is what we will attempt doing. First of all, I would like to teach you some basic notions, some fundamentals of multidimensional digital signal processing. So we'll start with continuous domain multidimensional signals. We'll learn one of the main workhorses of signal processing, the Fourier transform. Basically, we'll see different properties of this transform. Then we'll talk about sampling and interpolation. We'll see that when we go from one-dimensional signals to multidimensional signals, there are more interesting ways of doing sampling. And I will show you concrete examples where actually these kinds of non-trivial samplings work in real cameras, for example. Then we are going to talk about inverse problems. I will try to convince you that many image processing tasks can be formulated or can be approached as estimation problems. So we'll talk about estimation, and then our sort of holy grail will be to find a good prior, a good model for images. And we'll talk about different models. We'll do some very quick overview of different models, starting from ideas, very powerful ideas that have been around for about 20 years, like parsimonious representations, like how to represent an image or a signal sparsely in some dictionary of prototype images. And then we'll see the connection between these techniques and modern deep learning techniques, for example, convolutional neural networks. Then I will show you some ideas, some modern approaches to sampling and to computational imaging in general. I will say a few words now in this introduction. We'll see more. So I will briefly say a few words about myself, why I believe I can waste your time and basically tell you stories about image processing. So I did all my degrees in here at the Technion. Actually, I haven't been in this building for 20 years. It's quite amazing. It's still the same. So I was trained as an electrical engineer. All my teachers were electrical engineers, so my way of thinking is also similar to the way electrical engineers think. And this is maybe a little bit an outlier for people coming from the computer science background. So basically, we'll need to level at least some background, some mathematical background related to elementary harmonic analysis and things like that. I've been a professor of electrical engineering at Tel Aviv University. I moved to the Technion more than 2 years ago in 2016 to the computer science department, and my research interests are somewhere in the intersection of signal and image processing, computational imaging, computer vision, machine learning, computational geometry. And I've also been quite a bit in the industry. In particular, I participated in 3 startup adventures, all of them related to image and video processing. So in the first startup, we did a video processor, basically hardware for doing video processing. In the second startup, we actually did a lot of imaging. We built what is now Intel is branding as RealSense, basically depth cameras. And in the third startup, we are doing a video search engine. So basically, I have both theoretical and practical notion of image processing and related fields. And I will try to share my insights about this with you in this class. Okay? Yes, please. No, it's not. It's just for the recording. Yeah, I will try to raise my voice. Okay, so why shall we care about image processing, and why is it even more relevant today than it was, let's say, a decade ago? So first of all, if you have noticed, or I don't know if you know, basically all primates and Homo sapiens included, we see the world as mostly as visual sensory input. We have quite a big portion of our brain cortex dedicated to processing visual information, and therefore, basically, we see images. And from the dawn of the human civilization, we tried to communicate with images. This is one of the oldest cave paintings. So people tried to convey some story by painting it. But unlike language, the visual world is so overwhelmingly more complex in terms of the amount of information is required to describe it. Drawing a scene like this by hand will take us hours, right? So people have tried to invent techniques and technologies to try to capture the visual world in order to be able to communicate with pictures, right? Basically, this has been our goal forever. So one of such early attempts was basically building primitive optics, building primitive optical systems. So this device is composed of a screen with a small hole in it. So if we drill a small hole here and darken this room and put a screen in front of this small pinhole, we will see the world outside upside down. Okay, and this was named in the medieval times as camera obscura, Latin for a dark chamber. And actually there are earliest records suggesting that these kind of devices have been constructed more than 2,000 years ago. But basically this was widespread in Europe, at least by the beginning of the 18th century. However, so we can see the image of the world. We actually can use it as a device to assist painting. For example, Vermeer was allegedly using this kind of device to paint stunningly photorealistic pictures, like this one. So the perspective, the light is extremely accurate. And probably he was using a device like this in order to paint his paintings. But still, you need to spend hours behind this screen in order to capture the information from the world. So basically, you see an image, but it is not persistent, right? And it was probably around the 18th century that accidentally some chemicals were discovered that are photosensitive. So if you illuminate them with light, they change their properties and they for example become darker. However, these chemicals were also not persistent, and it was in the beginning of the 19th century that the photographic process was invented. So basically, a special sequence of chemical processes that first expose a chemical to light and then fix that set of changes that happened in this chemical in order to make the image persistent after the exposure is done. So this is one of the earliest surviving photographs, the beginning of the 19th century. The exposure time here was 6 hours. Imagine that you need to pose in front of a camera for 6 hours. This is, of course, completely unusable, but this was the beginning of photography. Okay? Of course, we made quite a long way from that. This was the first color photograph. And you can see that basically the colors are misaligned because the exposure was still incredibly long. And this is an imperfect process. This is the beginning of the 20th century. I think modern photographers will die for taking pictures like this. This was a Russian guy. Actually, he was taking three pictures on 3 separate films through color filters, and then he built a special projector to display them. This is not retouched. This is the original quality of the images. Okay. Of course, our world is not static, and the next step was to capture motion. And basically, this is the first surviving motion picture, the first surviving movie. It was not done by Frère Lumière. Frère Lumière were the first to commercialize cinema, and they did incredibly well. But still, you need to be seated in a movie theater in order to watch this, right? So the next step was to broadcast this over distance. And this was probably around the end of the 20s of the 20th century that electronic television was invented. Okay, so just imagine how this changed our life. Imagine, for example, how powerful this tool is for a politician or to divulge culture. to people. This completely changed our habits, our way of life. The next step was to record this signal on tape. So basically making ubiquitous, or actually a home appliance, the means of recording. So basically you see in the 30s, in the 40s, even in the 50s, all the broadcast was done live. There was no way to record TV signals on any medium. So basically, actors had to act in front of the camera that was transmitting the signal to everyone's home. But the next step was to basically to make this signal persistent, recording it on tape. This is one of the first video cassette recorders from the 70s. It's quite incredible how this technology, basically how late this technology was introduced. Still, editing movies, basically film and video, was more or less like this. So if you wanted to retouch the colors of an image, you actually had to paint it by hand with colors. It's a painstaking process. So basically, one of the reasons for going digital was the fact that once the image is represented in a digital format, editing and manipulation of the image becomes incredibly more powerful. Okay, so this was one of the first, or the first, digital image sensor. It was a charge-coupled device, CCD, invented by Boyle and Smith. This is the first Kodak CCD camera. Actually, Kodak is an incredible company. They invented digital photography, and in around 2010, they filed for Chapter 11 for bankruptcy because they didn't manage to transition the corporation from analog film to digital photography, and basically they just ran out of steam. Nobody needed film anymore. Now, the next step was making this device portable. Okay, so this is the first DSLR camera with a digital sensor sold around 95, built by Konica Minolta. The next step was making it affordable. CCD is an incredibly expensive device. The yield of these chips is incredibly low. So in 1995, Eric Fossum invented what is called active pixel, or CMOS sensors. CMOS is the technology that is used to manufacture practically 99%, probably I'm wrong, 99.9% of all chips that you encounter in the world. So this is a ubiquitous silicon semiconductor technology. It is very cheap. So building sensors using CMOS processes reduced their price by orders of magnitude. So then you can make cameras, digital cameras, ubiquitous. And do you know this thing? I feel that I'm too old because I know what this thing is. This is a floppy disk. So this digital camera from 97, made by Sony, was recording digital images, I think 1 megapixel on floppy disks. So basically it became ubiquitous. And by the beginning of 2000, cameras started being integrated into cell phones. They were not called smartphones anymore. It was dumb. It was just taking pictures and making calls. But this made cameras intimate. Probably a huge leap was done by people from Apple who 11 years ago introduced the iPhone. So basically we have a camera in our pocket now, and just imagine in less than 10 years how profound was the change in our culture, in our social habits, how we communicate with people. So people, astronauts that went to the moon took a few dozens of photographs, and every photograph was of incredible value. I think we share on social networks 10 times more in a single day without any particular reason. So we changed completely the way we communicate through images. This was basically the goal that our ancestors had tens of thousands of years ago. Okay? And editing now looks like this. So once we went to digital technology, you can Photoshop an image. And today it is very difficult to distinguish between real images and edited images. It's quite difficult. The editing is so natural. Some of this editing happens automatically without us noticing it. So if you, for example, take this device, besides the camera chip, there is another companion chip called ISP, image processing pipeline, that, for example, takes an image like this, taken in low light conditions, and makes it like this. And it happens completely automatically. We just see a better picture, and we don't know what is the raw information that goes on there. Okay. Now, we can say that it was an incredibly long journey with spectacular results that basically took us from camera obscura to this modern DSLR camera, right? The technology is incredible. We know how to manufacture great lenses. We know how to manufacture sensors. But conceptually, this and this is exactly the same thing, right? So we put a sensor behind a lens, and it projects an image of the world, right? This is conceptually exactly the same thing. Can we do better? Can we actually leverage our compute power, our knowledge of digital signal processing to build new camera concepts, completely different? Okay, and so basically, I think a great example of what can be done using signal processing is this example. So what you see here is the first CT scanner, one of the few examples where engineers were awarded a Nobel Prize in something, in this case in medicine. So this was the first prototype of CT. I will show you in the next 2 hours, I guess, at least fundamentally how it works. But the conceptually novel idea here is that what you get is not what you see. So basically, you illuminate an object with X-ray, with penetrating electromagnetic radiation, and you put a sensor on the other side, and you capture some information, right? This information, if I show it to you, you will see nothing. It will be garbage. Okay? It's completely unintelligible by human. But when you combine it with some computational process, you can actually reconstruct an image of what is inside our body. Okay, so this is an indirect way of imaging that involves computational processes in it, and this is one of the first instances of computational imaging. Okay, so basically we combine some analog hardware with signal processing in order to create images, and then we can do many interesting and smart things in the imaging process itself in order to by means of computational processing to get an image. Okay. One of the examples, for example, is to sense depth. So you can use, for example, arrays of cameras or a pair of cameras to assign or to measure depth information at every pixel in the image. Okay, and just imagine what new capabilities it brings. So this is one of the earliest images from the Intel RealSense technology. But for example, it gives you these capabilities. So here you can see a synthetic computer graphics character animated by human actors. So the actor is facing a depth sensor, in this case Intel's RealSense camera, and basically the motion of the face is transferred to this animated character. Okay, so basically until the existence of this technology, we had to put markers and then follow them with using some kind of RFID type of motion capture technology, very bulky, very costly, quite inconvenient because you need to cover all the face with markers. This is much closer to being natural. Another example, remember this movie? This was 2001, I think, Minority Report. Remember how revolutionary the human-machine interface looked like? So you don't need any device to communicate with computer, just communicate with gestures, right? You move your hands in the air. Again, if you have a 3D sensor, you can capture the 3D location of your hands or of your body very accurately, and then build human-machine interfaces based on these ideas. So less than 10 years after this movie, Microsoft Kinect was already doing this kind of human-machine interfaces. Another example, remember Matrix, the Matrix movie, the bullet time effect? You know how it was produced? A team with a rig of analog cameras capturing on film, incredible length of film that passes through this rig costs something like $500,000 for 1 hour of shooting, and this is the same effect 10 years later. So this is completely digital, a set of 10 calibrated cameras. This was done in the Olympics a few years ago. Was done by an Israeli startup company called Replay Studios that were acquired by Intel a few years ago. So again, this is done completely digitally. Now, we can do more interesting sensors, imaging sensors. For example, we can try mimicking nature. Some insects have what is called faceted or compound eyes. They have multiple lenses that make an image of the world from slightly different vantage points. Okay? So in one of the zoos in New Zealand, the organizers of an exhibition felt an urge to visualize to their customers how a honeybee would see the world. So this is more or less how it would see the world. So many tiny images, each coming from a small lenslet in the faceted eye. So if I show you this image, I don't think you will be able to make any use out of it. Okay, this is called a light field image. But if you combine this with computational processes, for example, what you can do, you can refocus an image after it has been acquired. So you acquire an image, and then you synthesize a new image that would be acquired by, let's say, a DSLR camera if it were focused on some depth. So you create this bokeh effect after the image was taken. And there are many, of course, many crazy things that can be done with computational image. There is actually a real device called lytro that does this. It was commercially, it was a flop, but still the idea of light field cameras is very powerful. Light field cameras, light field displays, they are an emerging technology nowadays. Okay, so I can tell you more stories about digital imaging and digital image processing, but hopefully you are more convinced that basically nowadays where digital images and digital photography have become our intimate companions, even without noticing we are using these technologies all the time. Let's try to at least understand how to manipulate images, how to do digital signal processing. Okay, so this was our motivation. And unless you have any questions, let's now move to the real stuff. Any questions? Yes. Yes. Not really. I think it is not even known how we reconstruct the image. So it is not even known how we humans reconstruct the image or how primates reconstruct the image. So it's quite difficult to study visual processes in the brain. So we definitely don't reconstruct a depth image, but we probably use some kind of depth clues coming from an intersection of two visual fields of both eyes to infer depth information. But again, these are very complicated processes. We know a lot about low-level image processing in the visual cortex. We know quite little about high-level processing. Okay, but yeah, I'm not a neurobiologist, and unfortunately I cannot tell you more about what is known nowadays about vision of these insects. But we can actually deconstruct and analyze the optical system, which looks more or less like this. Okay, any other questions? Okay, let's move to the real stuff.